You sit in your room, the hum of electronics filling the space around you, the familiar weight of gravity pressing your body into the chair. Time passes predictably. Objects maintain their form, and the laws of motion feel absolute. You assume the universe beyond your walls is similarly constrained, governed by rules that you can trace and anticipate. Yet somewhere beneath the controlled certainty of these assumptions, a signal has appeared. A particle detection at CERN, measured, verified, catalogued, a signal that should not exist under the framework that has guided particle physics for decades. No speculation, no theoretical fancy predicts it. It is real, undeniable, and internally consistent. Every instrument designed to obey and verify nature has confirmed it. You are faced with a contradiction, a physical phenomenon that is impossible by the standards of everything previously measured, yet undeniably present. It does not bend the rules in some obscure corner of theory. It violates them directly in the most precise and observable way. The signal challenges your assumptions about what particles, energy, and causality are allowed to be. It suggests that the universe may be fundamentally stranger, more layered, and less coherent than your experience implies. And so the question emerges, quietly but insistently: what does it mean when nature itself produces evidence that should not exist? The familiar world of particles. You think of particles as building blocks, the predictable components of reality. Electrons orbit, protons cluster, neutrinos flit through space unnoticed. They obey well-defined laws, confirmed through decades of observation. Yet the signal at CERN suggests a disruption, something present that refuses to fit the catalog. A particle behaving as if rules themselves are conditional. You have learned to expect stability at the smallest scales. Particle physics is a science of certainty. Mass, charge, spin, and decay modes are measured with precision. Detectors are tuned to observe the tiniest deviations, designed to capture anomalies as they ripple through fields and chambers. And yet, this signal did not merely register as a fluctuation. It appeared fully formed, persistent, consistent across multiple experiments, immune to the usual filters that dismiss statistical noise. The tools designed to confirm what is possible now record what should be impossible. This is not a failure of instrumentation. Every calibration, every cross-check, every control confirms the presence of the anomaly. Its energy, momentum, and decay patterns align with measurement standards, yet none align with the predictions of the standard model. You can trace it, quantify it, categorize it, but every category leads to a dead end. The particle exists in a liminal space, obeying the rules enough to be detected, but refusing the boundaries that make detection comprehensible. Consider the role of constraints in your understanding of reality. Particles are not arbitrary. They are bound by conservation laws, energy and momentum, lepton number, charge, and more. These constraints are the reason you trust the catalog of known particles. They are the reason predictions can be made with confidence. Then experiments can be designed with purpose. Yet this signal exposes a loophole, or perhaps a fracture, within those constraints. It acts as if the universe permits exceptions that are invisible until specifically observed, as if some rules only exist in the absence of this particle. You might ask how such a particle could exist without having been observed before. The answer lies in subtlety. It does not dominate interactions. It does not explode into visibility. Its footprint is narrow, precise, and easily overlooked unless instruments are tuned to the exact configuration. In this way, the particle is paradoxical, elusive yet measurable, forbidden yet present, invisible until revealed, and undeniable once it is. Even more unsettling is the implication for causality. If a particle can exist without conforming to established rules, then the sequence of cause and effect at fundamental scales may be less rigid than assumed. Interactions could occur in ways not predicted by prior theory, processes that ripple forward through time with constraints that are conditional, context-dependent, or hidden until measurement forces their revelation. The universe you trusted, where every effect can be traced to a cause and every particle obeys its classification, may be a simplified interpretation of a more complex substratum. The signal also challenges the relationship between observation and existence. You assume that measuring particles confirms their behavior. You trust that what is detected is what exists. But this anomaly suggests that existence and detectability may not coincide neatly. Some phenomena may remain dormant or invisible until the precise configuration of measurement brings them into being. Reality, in this sense, becomes interactive, shaped not only by particles themselves, but by the act of observation and the framework of instruments used to track them. Ultimately, this disruption forces a confrontation with the limits of understanding. You are accustomed to the idea that particle physics has mapped the fundamentals of matter. Every quark, lepton, and boson has its place, every interaction predictable within known equations. And yet, here is evidence that the map is incomplete. The world of particles is familiar only as long as it adheres to expectation. Once that adherence is broken, even in the smallest measure, the certainty of everything you have learned begins to unravel quietly, leaving you with a simple, disquieting realization. What you thought was fundamental may only be provisional. When measurement becomes contradiction, every instrument confirms what it detects. Every repetition reinforces certainty. And yet, when you examine the data, what emerges is internally consistent, but globally incompatible. The signal obeys the constraints of one system while defying the constraints of another, revealing a tension embedded in measurement itself. You expect that repetition will produce agreement. This is the principle on which all experimental science rests. The same conditions yield the same outcomes. Detectors are calibrated to a degree that allows subatomic events to be recorded reliably. Statistical analyses filter noise from signal, and the methods have been refined over decades to eliminate ambiguity. The signal at CERN conforms to every one of these criteria. It is measurable, reproducible, and statistically significant. Nothing about its detection suggests error, yet the contradiction appears when you step back and consider the broader framework. Within a single detector, the signal behaves precisely as the laws of conservation demand. Its energy and momentum balance, its decay products align. Within this local system, it is legitimate. Outside of this context, when compared with other measurements and theoretical predictions, the particle violates expectations. Its existence implies processes that should redistribute energy or influence other particles in ways that are not observed. The local and global realities clash. This tension challenges the assumption that measurement merely reflects reality. Observation is supposed to map a world that exists independently of instruments. Yet here the act of measurement seems to expose an inconsistency inherent in the system itself. The data are correct, but the framework in which they are interpreted cannot fully accommodate them. The signal is simultaneously real and inexplicable, obeying rules that are valid only in the context of the detecting apparatus. Consider the mechanisms at work. Conservation laws, symmetry principles, and quantum constraints are not violated in a local sense. Within the chamber, the particle fits the expected pattern. Yet these laws are meant to be universal. When the same event is extrapolated to the scales of the standard model, contradictions emerge. Momentum that should be conserved across interactions appears to vanish. Expected correlations between particles fail to materialize. Repetition confirms the anomaly, not just once, but across different experimental setups, reinforcing that the inconsistency is not an artifact of a single instrument. The implication is subtle but profound. Measurement itself may reveal limits in your models of reality. You have assumed that accuracy and consistency are sufficient to define understanding. They are not. The particle demonstrates that an observation can be coherent locally while incompatible globally. It is a reminder that what is measurable may not always align with what is permissible in theory. Reality, in this sense, is conditional, revealing contradictions only when carefully probed. Even the notion of causality becomes strained. If the signal adheres to conservation laws within one framework but disrupts them in another, then cause and effect relationships cannot be assumed to operate universally. A particle's behavior in one detector may not fully predict its consequences in a larger system. Local interactions are governed, global consequences are not. The universe is behaving like a system with embedded loopholes, revealing fractures in the architecture of what you thought was a seamless, deterministic network of rules. There is also a temporal dimension to the contradiction. Every repetition over time reproduces the same result. The signal does not dissipate, it does not fluctuate into randomness, yet the contradiction does not resolve with time either. The persistence of the anomaly implies that these embedded tensions are stable features of reality, not ephemeral deviations. The universe permits conditions that are both predictable and paradoxical simultaneously. Ultimately, the observation forces you to confront an uncomfortable reality. Instruments confirm the particle, theory cannot. Consistency in measurement does not guarantee comprehensibility. You are left with a scenario in which what you see is undeniable, yet what you understand remains incomplete. The contradiction is embedded, unavoidable, and irreducible. It exists in the interface between observation and principle, revealing that even the act of measurement exposes limits in the coherence of your knowledge. Energy, where there should be. None you expect energy to follow conservation laws, to appear and disappear in predictable exchanges. This signal appears as an excess, not a fluctuation, not noise. Its presence is a breach of expectation, measured by the very tools designed to quantify and limit energy precisely. Instruments calibrated to detect the subtlest shifts register an anomaly that refuses to vanish under scrutiny. It persists, unyielding, almost deliberately defying the framework that defines what is physically possible. Every attempt to rationalize it encounters a wall, perhaps a hidden particle, an undiscovered form of matter, or an overlooked interaction is at play. But conventional models fail to accommodate the scale and nature of this surplus. It does not behave like heat, light, or kinetic energy. It is something else entirely, a spectral shadow of what energy should be. Its signature is unmistakable, yet inexplicable. Like a ghost in a cathedral of physics, it lingers where theory predicts only emptiness. The implications are profound. Conservation laws are among the most tested principles in physics, guiding every experiment, from tabletop quantum setups to the detectors buried deep underground. These laws are not mere convenience. They are the skeleton upon which all models of reality are hung. To encounter energy in violation of these principles is to confront the possibility that something fundamental is incomplete, that our understanding of the universe is provisional, perhaps even naive. If energy can exist where it should not, then the rules we trust to govern motion, decay, and interaction are no longer absolute. They are local, emergent, or context-dependent. Researchers initially questioned their own instruments. Could a calibration error, a cosmic ray, or an environmental interference explain the excess? Each possibility was eliminated methodically. The readings were consistent across different devices, in different laboratories, under different conditions. The anomaly does not belong to a single experiment. It transcends setups, as if the universe itself were whispering a secret the equations had yet to learn. The phenomenon also challenges assumptions about emptiness. What is a vacuum, if not a stage for particles to dance according to strict rules? Yet here, energy appears in the void, uninvited and unaccounted for. The vacuum, long considered the baseline of nothingness, reveals itself to be more intricate, more active, more mischievously alive than anticipated. This realization hints at an underlying structure or mechanism, something woven into reality that remains invisible until probed by sufficiently sensitive eyes. It is a reminder that absence is never absolute, and that nothing may carry potentials we are only beginning to glimpse. Speculation abounds, ranging from the mathematically rigorous to the wildly imaginative. Some theorists suggest a connection to dark energy, that mysterious force accelerating the universe's expansion. Others consider quantum field fluctuations, virtual particles that somehow manifest persistently rather than fleetingly. Exotic ideas, like energy leakage from parallel dimensions or the imprint of a hidden topology in space-time, gain traction precisely because conventional explanations fail. None are confirmed, yet each points toward a startling truth. The cosmos is not obliged to behave as expected, and our certainty is provisional. This signal, small yet persistent, is a subtle disruption with enormous consequences. It is a puzzle without a known solution, a test of patience and intellect for those who study it. Its presence is both a challenge and an invitation, a reminder that discovery often arrives as contradiction, and that reality's depth is measured not by what conforms, but by what resists comprehension. In the quiet readings of highly sensitive instruments, energy dares to exist where it should not, and in doing so, it asks us to question the very foundations of what we believe is possible. The quiet anomaly. No explosion, no dramatic event, no sudden upheaval. The anomaly is quiet, passive, yet its effects are measurable across multiple detectors. Reality often hides contradictions in subtlety, and here it speaks softly but clearly. In a universe accustomed to extremes, supernovae, gamma-ray bursts, the colliding galaxies. The notion of an anomaly that whispers rather than shouts is almost unsettling. It is not absence that marks it, but presence in a form that defies conventional classification. Instruments detect shifts, fluctuations, and deviations that seem to persist without origin or purpose. The data cannot be dismissed, yet it refuses to fit established patterns, teasing the boundaries of expectation. Across different observatories, the signature is consistent yet puzzling. Radio waves oscillate slightly out of phase with predicted models. Gravitational readings suggest mass distributions that do not correspond with any visible matter. Even the faintest photon counts deviate from what should be statistically probable. Scientists trained to find causality and narrative in the cosmos find themselves tracing shadows. The anomaly does not announce itself with grandeur. It is a whisper in the symphony of cosmic activity, subtle yet unignorable. Each measurement confirms the presence of a force, effect, or phenomenon that refuses to be fully explained, leaving theoretical frameworks incomplete. Attempts to simulate it in laboratories yield partial echoes of the effect, but never the full phenomenon. Computer models, even when fed every known variable, cannot reproduce the persistent subtlety observed. Hypotheses multiply. Quantum fluctuations on macroscopic scales, dark matter interactions, emergent gravitational irregularities. Each provides insight, but none encapsulates the entirety of the observation. The anomaly exists at a threshold where measurement, interpretation, and expectation converge and conflict. It challenges assumptions about scale, the causality, and the very fabric of reality. Scientists are compelled to redefine what anomaly means. It is no longer just a deviation. It is a clue to the deeper architecture of existence. Interestingly, its quiet nature amplifies its impact, because the anomaly does not overwhelm. It forces prolonged observation, patient scrutiny, and careful synthesis. Unlike spectacular cosmic events that dominate attention and narrative, this anomaly demands humility and persistence. Researchers spend weeks, months, sometimes years, collating datasets, cross-referencing instruments, and running statistical models. Each confirmation deepens the enigma. The anomaly's effects are real, repeatable, and measurable, yet their origin remains obscure. It is as though the universe has hidden a note in its own structure, audible only to those willing to listen intently, without expectation of immediate revelation. Philosophically, the anomaly carries implications beyond physics. It invites reflection on the nature of knowledge itself, the limits of perception, and the interplay between observation and reality. If something so subtle can leave measurable traces, what else might exist beyond the reach of our current instruments? Are there layers of reality that operate quietly, shaping events and structures without our recognition? The anomaly suggests that the cosmos is not merely a stage for dramatic events, but a complex, interwoven system where even the faintest perturbations hold significance. In this quietness, the universe communicates its complexity, reminding observers that understanding is incremental, emergent, and often counterintuitive. And ultimately, the quiet anomaly is a testament to the unexpected ways the cosmos challenges comprehension. It does not demand attention through spectacle. It commands it through persistence, subtlety, and the relentless refusal to conform. In listening to the quiet, observing the imperceptible, science finds both frustration and inspiration. The The anomaly does not resolve neatly. It never explodes into clarity, but it reshapes the contours of inquiry, nudging the mind toward new conceptual horizons. In its silent presence, the universe reminds us that sometimes the loudest truths are whispered. Symmetry and its fracture. You assume the universe favors symmetry. Laws apply equally, particles behave in mirrored ways. Yet this detection suggests a fracture, an asymmetry that cannot be reconciled with standard models. Symmetry exists, but only in a local sense, collapsing when observed in combination. This fracture is subtle yet profound. It is not the kind of asymmetry we see in everyday life, like the difference between left and right hands, nor is it merely a statistical fluctuation in experimental data. It is a structural divergence, encoded in the very fabric of reality. Physicists often rely on symmetries to simplify complex interactions. Conservation laws, invariances, gauge symmetries. These are the scaffolding of prediction. But when symmetry fails, that scaffolding wavers. Predictions that once held become conditional, reliable only within limited domains. The consequences ripple through multiple layers of understanding. At the particle level, quarks and leptons no longer behave as perfect mirror images. Matter and antimatter, expected to annihilate symmetrically, leave behind unexpected residues. Some interactions favor one direction over another, introducing a bias that has implications for the formation of galaxies, the distribution of cosmic background radiation, and even the evolution of large-scale structures. The universe, it seems, has preferences, hidden inclinations that standard models cannot account for. On a larger scale, this asymmetry challenges the notion of isotropy, the assumption that the universe looks the same in all directions. Telescopic surveys and cosmic microwave background measurements suggest subtle deviations, patterns that hint at an underlying fracture. These are not massive distortions, but slight irregularities that grow significant when integrated over cosmological distances. They suggest that symmetry, while a guiding principle, is conditional, fragile when subjected to the cumulative effects of vast scales. Theoretical frameworks struggle to accommodate this. Supersymmetry, long proposed as a unifying concept, predicts elegant balances that simply do not appear in observation. String theory offers a landscape of possibilities, but even there, the predicted harmonies of vibrations do not explain the asymmetry manifest in our corner of the cosmos. The discrepancy is not just a matter of missing particles or unobserved forces. It is a fracture in expectation itself. Our equations, our neat mathematical symmetries, or approximations of reality rather than perfect mirrors of it. This realization carries philosophical weight. Symmetry has long been equated with beauty, a hallmark of simplicity and intelligibility. The universe was presumed to be orderly, its laws harmonious. The discovery of fracture introduces an intrinsic unpredictability, a sense that order is provisional. In practical terms, it forces scientists to reconsider how constants are defined, how initial conditions propagate, and how fundamental interactions are constrained. What was assumed to be a universal principle may only be a local convenience, valid only where observations happen to align. Experimentalists confront this challenge with both awe and frustration. Detecting asymmetry requires exquisite precision, isolating noise, distinguishing between statistical anomalies, and genuine deviations, and reproducing measurements across independent experiments. The data hint at a hidden structure, a rule set that governs exceptions rather than absolutes. And understanding it may demand a paradigm shift, one that reframes symmetry not as an absolute, but as a phenomenon that emerges contextually. Ultimately, the fracture in symmetry suggests that the universe is simultaneously regular and irregular, predictable yet stubbornly biased. It is a cosmos where rules exist, but their applicability is limited, contingent upon scale, perspective, and interaction. Symmetry is present, but it is not sovereign. It is a local guest in a universe that prefers in subtle ways to break its own mirror. The challenge now is to map the fracture, to discern the principles behind the asymmetry, and to integrate them into a coherent picture of reality. A picture that embraces imperfection as fundamental rather than incidental. Time's subtle distortion. Time is expected to flow uniformly, its arrow consistent across all interactions. Yet this signal appears to violate temporal expectations, suggesting an interaction that precedes its cause or lingers beyond its decay, quietly challenging the linearity of time you assume is absolute. This anomaly does not announce itself with a dramatic rupture or a catastrophic failure of physical law. It is subtle, almost imperceptible, detectable only through the accumulation of observations that contradict the neat, sequential model that underpins classical reasoning. The effect is like a whisper, a hesitation in the universe's otherwise relentless march, hinting that time may not be the one-dimensional parameter it appears to be. Consider the behavior of particles in extreme gravitational fields. Near the event horizon of a black hole, clocks tick differently, not because the universe has paused or accelerated in a global sense, but because the local passage of time is warped by space-time curvature. Even photons, massless carriers of light, trace paths that reflect the bending and stretching of temporal intervals. These distortions are measurable, yet they feel alien to intuition, which assumes that cause and effect proceed in a strictly ordered chain. What is striking is not the presence of these distortions, they are predicted by relativity, but their persistence in domains where classical expectations should hold, suggesting that the rules governing time may be layered, context-dependent, and relational rather than absolute. In laboratory conditions, similar effects emerge, though on scales far smaller and far less dramatic. Quantum entanglement, for instance, allows correlations between particles separated by distances where light could not travel fast enough to mediate the interaction in a linear time frame. Information about the state of one particle seems to reflect in the other instantaneously. There is no violation of relativity here, because no usable signal travels faster than light, yet the effect challenges the concept that temporal ordering is strictly local. The entangled system behaves as if the past and the future are not strictly partitioned, as if some aspect of time is shared across what we perceive as independent events. Your perception of temporal flow, similarly, is a construct. Biological clocks, psychological sequencing, and societal conventions impose order on phenomena that, at the fundamental level, may not require it. In this sense, time is both objective, measurable by instruments, and subjective, shaped by the way observers interact with the world. The discrepancy between these two is rarely significant in daily life, but in the extremes probed by modern physics, it becomes unmistakable. The universe does not necessarily align with the expectations formed by human intuition. Temporal order can be skewed, reversed, or diffused, and yet the cosmos continues unperturbed, indifferent to the linear narrative you impose. This is not a failure of physics, but a revelation of its depth. Time, like space, is more flexible than it appears. Linear sequences, past and future, beginnings and endings, are emergent patterns imposed on a continuum that may be fundamentally relational and multidimensional. The universe operates according to rules that permit subtle deviations from strict causality, yet these deviations are consistent with deeper symmetries and invariances that maintain coherence across scales. Understanding these distortions requires abandoning absolute certainty in favor of a more nuanced perspective, one that treats time not as a single, uniform river, but as a tapestry of interwoven threads, each capable of stretching, looping, or overlaying with others in ways that remain largely invisible until the right lens reveals them. Ultimately, the subtle distortions of time you observe are reminders that even the most familiar dimensions are subject to profound surprises. Time is not broken, nor chaotic. It is simply more intricate than the linear narratives you construct around it. These anomalies invite reflection, demanding that you reconsider the assumptions that govern the very framework of experience. They whisper of a universe in which chronology is not a given, but a property that emerges, bends, and occasionally defies, hinting at a temporal landscape as complex and mysterious as the cosmos itself. The shadows of the Standard Model. The Standard Model has been your map of reality, its equations precise and predictive. But the map cannot contain this signal. It lies outside established frameworks, like a shadow beyond the edges of the charted landscape, measurable yet unmapped. You have relied on this model to define what is possible at the most fundamental scales. It catalogs quarks, leptons, bosons, and the interactions between them. It predicts decay patterns, collision outcomes, and the forces that govern these processes with extraordinary accuracy. In its domain, the universe appears coherent, governed by rules that are symmetrical, consistent, and mathematically traceable. This framework has shaped decades of research, experiments, and technological applications. It has become, in essence, the lens through which you view reality. And yet, the signal defies this lens. It is real, measurable, and persistent, but it cannot be accommodated within the Standard Model's equations. The particle does not align with predicted families. Its energy levels do not match anticipated mass ranges, and its interactions do not follow any known conservation rules beyond the local context. It behaves as if existing just outside the boundaries of the map, visible only when observed with instruments precise enough to capture it. This is not a subtle deviation. It is a clear demonstration that the Standard Model, as comprehensive as it seems, is incomplete. The anomaly occupies a liminal space, at once constrained enough to be recognized as a particle, yet unconstrained enough to evade categorization. Its existence suggests there may be dimensions, interactions, or principles that the current model cannot describe. Phenomena that were always present, but invisible until this precise configuration of measurement revealed them. You might consider the philosophical weight of this. The standard model is often treated as definitive, the final statement on subatomic matter, short of new, revolutionary discoveries. Its shadows, gaps, unexplained constants, anomalies, have been largely theoretical, tolerated as limitations to be resolved eventually. But now, when one of these shadows has materialized as empirical evidence, what was once a theoretical boundary is now a tangible disruption, an unmapped region that exerts influence yet refuses classification. The signal exposes an unsettling tension between measurement and theory. It obeys laws locally, yet the global framework cannot accommodate it. Within the chamber, energy and momentum appear consistent. When extrapolated to a wider context, it produces discrepancies, inconsistencies that cannot be ignored. The shadow of the standard model is no longer abstract. It is a domain where observation and prediction diverge, where reality manifests beyond the grasp of existing principles. Even symmetry, the principle that underlies much of the standard model, is challenged. Parity, charge, and other expected symmetries are disrupted in ways subtle but measurable. The particle occupies a space that is neither violation nor compliance. It is a liminal existence, a presence that the rules anticipate only in absence. The model describes what is allowed, yet this particle is allowed only in defiance of the model itself. This has implications for how you think about the structure of matter. If the standard model's map is incomplete, the universe is not only more complex than assumed, it is layered in ways invisible to conventional instruments. Shadows exist not merely as conceptual gaps, but as regions where new phenomena can emerge, detectable only when probed with precision and attentiveness. The signal is a reminder that what you treat as a complete system is provisional, a surface-level understanding of a far deeper, more intricate reality. In the end, the anomaly forces a quiet reckoning. The standard model is extraordinarily powerful, yet here it reaches its limits. The shadow at its edges is not empty. It is occupied, measurable, and consequential. You are left with a map that is precise where it applies but fundamentally incomplete, and with the realization that the universe may always harbor regions beyond comprehension, domains where observation reveals presence, but understanding lags behind. Causality without comfort. You believe in cause and effect. Events produce consequences in predictable sequences. This particle appears to exist independently of expected causes, a measurable effect without a traceable origin, unsettling the foundational logic of how interactions propagate. Instruments register its presence reliably, yet no preceding event accounts for it. It is an effect without a known cause, a ripple in the cosmic pond with no stone to explain its formation. The very principle that underpins observation, prediction, and scientific reasoning trembles in its presence. Physicists first assumed error. Perhaps the detection was spurious, a glitch in the equipment, or a misinterpretation of background signals. Each suspicion was eliminated through repetition and cross-verification. Different instruments, different laboratories, different conditions, all reproduced the same anomaly. The particle appears again and again, stubbornly indifferent to skepticism. Its behavior is consistent, yet its provenance is absent. In a universe that thrives on interconnected sequences, here lies a breach, an event that refuses to acknowledge the chain of causation, in the ghostly exception to the rules that govern everything else. The implications are profound and unsettling. Cause and effect are not just practical tools, they are conceptual scaffolding. They allow for prediction, intervention, and understanding. Without them, the edifice of knowledge loses its firm foundation. If a measurable entity can appear without a causal antecedent, then the linear narrative of events, the story of how the universe evolves from moment to moment, is incomplete. Predictability, once considered a default of nature, becomes provisional, contingent, and perhaps local rather than universal. This anomaly forces a reconsideration of what it means to exist in the universe. Does this particle have a hidden origin that is fundamentally undetectable? Or does it suggest that effect can sometimes manifest independently, emerging spontaneously from the rules themselves? It challenges the intuitive idea that the universe is a smooth, coherent tapestry of interactions. Instead, it hints at pockets of behavior that are untethered, islands of consequence appearing without an anchoring cause. Even the vacuum, long considered a passive stage for events to unfold, seems to participate in subtle ways that defy classical reasoning. Speculation naturally arises. Could this be a manifestation of retrocausality, where future states influence the present? Might it be an imprint of higher dimensional processes, interactions occurring outside the familiar space-time we occupy? Or is it evidence of an emergent rule, set in which causality itself is probabilistic, not deterministic? Occasional exceptions embedded in the universe's fundamental laws. Each hypothesis stretches understanding, yet none are presently confirmed. The particle exists independently of explanation, a stubborn fact that refuses to yield to comforting narratives. The psychological impact on researchers is almost as significant as the theoretical implications. Humanity relies on patterns, sequences, and cause-effect reasoning to make sense of experience. To observe events that break this pattern is disorienting. It forces a confrontation with the idea that the universe may not be fully comprehensible through familiar logic. It raises uncomfortable questions about control, predictability, and the limits of knowledge itself. Ultimately, this particle embodies a disquieting truth. Causality, the foundation of comprehension, is not absolute. In the quiet hum of laboratories and the meticulous recording of data, the universe delivers a lesson in unpredictability. Events may unfold without precedent, effects may appear without cause. Logic may hold only locally, leaving us to navigate a cosmos where certainty is rare and anomalies are fundamental. In this disordered space, our expectations of linearity and coherence offer little comfort. Causality without comfort is not just an observation, it is a reminder that reality may be stranger, more intricate, and less obedient than any framework we impose upon it. Interaction without explanation. When particles interact, energy, momentum, and spin exchange predictably. The signal engages, collides, yet the results cannot be traced through known processes. It behaves as if a rulebook exists that has never been opened. Classical expectations fail, quantum predictions falter, and yet the phenomenon persists with consistency. Instruments record collisions, deviations, and emergent patterns, all unmistakably real, yet stubbornly outside the framework of established physics. It is not chaotic, it is coherent. But the coherence follows an invisible logic that refuses definition. Across experimental platforms, the signature emerges again and again. Particle detectors sense fluctuations that cannot be reconciled with known forces or interactions. Energy appears to transfer along uncharted pathways, and momentum seems redistributed in ways that violate anticipated conservation rules. The effect is subtle enough to evade casual observation, yet robust enough to be confirmed repeatedly. Researchers find themselves measuring, modeling, and remeasuring each dataset, affirming that something fundamental is happening in something that cannot be reduced to any familiar mechanism. The phenomenon resists simplification. While certain aspects resemble known particle behaviors, scattering angles, spin correlations, or energy dissipation, the overall interaction refuses categorization. It suggests an underlying architecture to the cosmos that is partially hidden, operating according to principles yet undiscovered. Like shadows cast by an unseen object, the interactions hint at a deeper order, an uncharted framework that structures energy and motion without ever announcing its presence directly. Scientists speak in cautious terms: anomalous coherence, hidden channel interactions, or non-classical mediation. Yet these labels serve only as placeholders for a reality that defies verbal or mathematical capture. Simulations and theoretical models offer partial insight, but they fail to replicate the full scope of the behavior. Even when physicists introduce hypothetical forces, extra dimensions, or exotic fields, the resulting predictions match fragments of observation, never the complete signal. The anomaly appears to exist in a liminal space between theory and observation, a place where the known laws of nature provide scaffolding but cannot account for the entire structure. It challenges the very notion of causality and forces reconsideration of what interaction truly means. Remarkably, the subtlety of the phenomenon magnifies its significance. Unlike high-energy collisions that reveal new particles in dramatic flashes, this signal requires patience, precision, and accumulation of data over long periods. Its persistence in the absence of clear mechanisms suggests that the universe may host processes that operate quietly, without spectacle, yet with profound consequences for the structure of matter. It is a reminder that not all truth is loud, and that understanding sometimes emerges from the careful tracking of the barely perceptible. The philosophical implications are equally compelling. If interactions can occur outside the purview of known rules, then the cosmos may be structured on multiple tiers, some accessible to measurement, others implicit, acting as hidden scaffolds upon which observable reality is built. It forces a reconsideration of determinism, causality, and even the limits of scientific knowledge. Observation alone is insufficient. Inference and imagination must join experiment to approach comprehension. The universe, in this sense, appears not as a fully legible text, but as a manuscript with blank pages and marginal notes, some of which hint at principles yet unarticulated. Ultimately, this interaction without explanation is both a challenge and an invitation. It destabilizes confidence, yet sparks inquiry. It defies the known, yet illuminates pathways to deeper understanding. In every subtle deviation, every anomalous scattering, it whispers the possibility that our grasp of the universe is provisional, that the map of natural law is incomplete, and that reality is far richer than the rulebook we have so far uncovered. It is a reminder that the pursuit of knowledge is not only about discovering, what is visible and measurable, but also about tracing the faint outlines of what has yet to reveal itself. The geometry of the impossible particle. Physics assumes space-time provides a backdrop, a framework within which all interactions unfold. This detection implies a distortion of that framework, as if the geometry itself allows modes of existence previously forbidden. Space-time, long treated as a smooth continuum, appears here to fold in unexpected ways. Traditional models rely on predictable curvature, dictated by mass and energy through general relativity. But the anomalies observed suggest pockets of space where geometry bends beyond these rules. Paths that particles traverse no longer correspond to classical geodesics. Distances stretch or contract unpredictably. The universe, it seems, has hidden dimensions of behavior, subtle twists that permit phenomena deemed impossible under conventional assumptions. And these distortions are not arbitrary. They manifest in measurable effects, shifts in particle trajectories, energy levels that defy prior calculations, and interactions that should be forbidden, yet occur with a quiet persistence. Such irregularities hint at a geometry that is probabilistic, not fixed, an architecture that can vary locally, permitting exceptions that ripple outward to influence larger structures. What was once considered a boundary, a hard limit of possibility, now seems negotiable. At the quantum scale, this has profound consequences. Particles exhibit correlations that defy conventional spatial reasoning, tunneling through barriers that classical geometry would forbid. Entanglement and superposition take on new meaning. The very stage upon which these effects play is no longer neutral. The space-time itself becomes an active participant, a variable in the equations rather than a passive container. In some regions, the geometry appears to permit states that should collapse under standard quantum mechanics, challenging the notion that fundamental rules are absolute. On cosmic scales, the implications are equally unsettling. Light from distant galaxies sometimes follows paths inconsistent with the simplest curvature models. Gravitational lensing occasionally produces deviations the standard relativity cannot fully explain, hinting at underlying distortions in the space-time fabric. The universe, rather than being a fixed grid upon which events unfold, seems to have elasticity, flexing and twisting in response to unknown influences. Observers can measure its effects, but they cannot yet predict its full behavior. Mathematically, accommodating this impossible geometry strains existing frameworks. Differential equations, tensor calculus, and even advanced topology can only partially describe the observed phenomena. The notion of a universal metric becomes conditional. Different regions may obey subtly different rules. Some theories propose a fractal-like structure underlying space-time, where geometry repeats irregularly at multiple scales. Others suggest hidden dimensions, folded so tightly that they influence reality without being directly observable. Both approaches acknowledge the same truth. The classical assumptions about uniformity and smoothness are no longer sufficient. Philosophically, this challenges the foundation of physical law. If geometry itself can bend in ways that permit new possibilities, and then impossible is no longer an absolute. Constraints thought intrinsic to the universe may instead be emergent, local phenomena. Science, which relies on predictability, faces a subtle but profound instability. The rules themselves might be contingent on geometry's hidden structures. The universe is not merely a stage, it is an evolving architecture capable of surprising its observers. Experimentally, the detection demands meticulous verification. Observing distortions in space-time requires extreme precision, isolating subtle shifts from noise, and confirming reproducibility across independent systems. Yet each confirmation reveals new layers of complexity. The more we probe, the more the geometry resists simplification. This is not a flaw in measurement. It is a reflection of the universe's underlying character, the reminder that the cosmos contains structural features beyond any prior imagination. Ultimately, the geometry of the impossible forces a re-evaluation of possibility itself. Space-time is not merely a canvas for matter and energy. It is a dynamic, malleable medium capable of supporting phenomena previously excluded by theoretical constraints. The challenge is not only to map these distortions, but to understand their rules, to translate the universe's subtle deviations into coherent principles. Reality, in this sense, is not fixed, but contingent, a landscape shaped by geometry that defies expectation, where the impossible may be quietly, persistently real. Noise that isn't noise. Experiments generate background noise, random fluctuations that must be filtered. The signal is not noise, it possesses consistency, pattern, and statistical validity. Its very clarity reveals that what you thought was impossible has entered measurable reality. At first, the mind resists. Your instincts categorize unexpected readings as artifacts, equipment errors, or mere coincidences. Yet repetition confirms their persistence. Across instruments, methodologies, and locations, the phenomenon endures. This persistence is itself a signal, a quiet declaration that the universe is offering information previously hidden. Information that obeys laws you had not anticipated. Closer inspection reveals structure within the pattern. Peaks and troughs, once dismissed as erratic, follow precise intervals. Correlations emerge between variables that by classical expectations should be independent. There is a rhythm to the data, subtle but unmistakable, a signature of order beneath apparent randomness. The implications ripple outward. What had been assumed as background, as trivial interference, now demands interpretation. The distinction between signal and noise becomes more than technical. It becomes epistemological. Your definitions of certainty, reproducibility, and significance are tested. The signal challenges not only measurement, but expectation. The universe has long permitted phenomena that appear anomalous when viewed from narrow assumptions. Radio waves, once inaudible and unexplored, became carriers of information. Quantum fluctuations, once imperceptible, now shape entire technologies. In the same vein, this pattern, this noise that isn't noise, forces reconsideration of what is accessible to observation. Its existence suggests that reality contains layers, some hidden until the precision of observation aligns with the subtlety of the effect. In this sense, clarity is not an artifact of the instrument, but a revelation of the universe itself. Equally striking is the universality of the signal. Variants of it appear in experiments conducted under different conditions across disciplines and scales. The coherence is statistical, yet undeniable. It cannot be attributed to local interference or coincidental alignment. Instead, it hints at principles that are pervasive, perhaps even foundational. If one signal can persist against the backdrop of expected chaos, it is reasonable to assume that others may exist, waiting for detection. The universe may be far richer in accessible phenomena than classical intuition allows, but your understanding of probability, randomness, and determinism must expand to accommodate this new evidence. This is not mere anomaly hunting. It is an invitation to explore the boundary between the measurable and the dismissed, between certainty and assumption. The process is meticulous. Patterns are verified, correlations are tested, statistical significance is quantified. Every apparent irregularity is scrutinized until the line between accidental and meaningful is rigorously drawn. In doing so, the signal asserts itself with undeniable authority. It is real, it is measurable, and it cannot be ignored. Ultimately, what you once labeled noise has become a lens into a subtler reality. The world you thought you understood, the universe of predictable interactions and tidy cause and effect chains, is incomplete. There exists an undercurrent of structure that defies dismissal, one that requires attentiveness, patience, and openness. The signal, persistent and precise, whispers of unseen mechanisms and hidden orders, inviting you to look deeper, to reconsider, and to recognize that the cosmos is far more intricate than your previous frameworks allowed. In the end, the clarity of the pattern confirms what was previously inconceivable, that reality can speak in whispers that resemble randomness but carry profound truth. What was dismissed as noise is in fact an expression of the universe's deeper order, a hidden dialogue awaiting those willing to perceive it, measure it, and understand it. It reminds you that measurement is not merely about observation, but about revelation. In this signal, the impossible becomes tangible, and the faintest hint of the extraordinary becomes unmistakable. Repetition and reliability. Every repetition of the experiment yields the same result. The signal does not vanish. It persists. Your instruments do not fail. Your models do not predict it. Persistence confirms reality, yet the contradiction deepens. You assume that repetition is a path to certainty. Science relies on it. Repeated measurements reduce error, refine parameters, and reveal patterns that might otherwise be obscured. A particle detected once could be dismissed as noise, an anomaly, or a miscalibration. Twice, it demands attention. 10 times, it forces acknowledgement. And yet this signal has persisted through scores of repetitions, across independent detectors, and under varying experimental conditions. Its consistency cannot be explained by chance or error. The persistence is deceptively simple, almost mundane. There is no sudden eruption of energy, no dramatic spike that forces immediate notice. It is quiet, steady, measured. And it is precisely this steadiness that amplifies the paradox. Every confirmation strengthens the credibility of the observation while simultaneously highlighting its incompatibility with existing theory. The more reliable the measurement, the more apparent the impossibility of the phenomenon becomes. Consider what repetition implies. Each instance is independent in terms of experimental setup, yet the signal behaves identically. This suggests that its existence is not a local artifact, nor a consequence of temporary conditions. It is embedded in reality itself. Instruments do not generate it, they reveal it. Its repeated appearance across independent systems demonstrates that the universe is capable of producing phenomena that are both consistent and unexplained. The anomaly is not a statistical aberration. it is a reproducible feature of the cosmos. Persistence also challenges assumptions about probability. You expect rare events to be fleeting, to fluctuate, to average out across repetitions. This signal defies statistical expectation. It occupies a regime where probability and occurrence diverge. A low probability outcome becomes a reliably observed event. The rules that govern likelihood appear insufficient to describe its behavior. In doing so, the signal forces a reconsideration of what probability means at fundamental scales, and whether universality can be assumed in processes you thought were well understood. Repetition interacts with your understanding of causality as well. If each detection is consistent, then causation must operate within a framework that allows stability, yet your theoretical models cannot account for the mechanism. The particle persists without a known origin. Its repeated appearance, hinting at processes outside the causal chains currently recognized. Repetition affirms existence, but it does not resolve the underlying paradox. You observe the effect, yet the cause remains concealed. Even the instruments themselves become part of the anomaly. Their reliability is no longer neutral. It serves to amplify the contradiction. Each detector, each measurement, each calibration reinforces the signal, confirming that reality behaves differently than expected. What is usually a source of certainty, the reproducibility of experiments, here becomes evidence of the universe's unpredictability, demonstrating that consistency does not necessarily equate to comprehensibility. Finally, persistence stretches the temporal dimension of the anomaly. Weeks, months, and repeated cycles of experimentation reveal no decay in the signal's behavior. It is stable in time, as if the universe allows contradictions to endure indefinitely. Observation is not a fleeting interaction, but a sustained dialogue with a phenomenon that refuses to reconcile with expectation. The very reliability that should comfort you now produces unease. The particle is real, persistent, and undeniable. Yet its existence undermines the frameworks that you depend on to interpret it. In the end, repetition does not simplify, that it confirms reality while exposing its limits. It reveals that certain phenomena, once detected, are not anomalies to be dismissed, but enduring contradictions woven into the fabric of the measurable universe. The signal persists, and in that persistence lies both clarity and disquiet. Reality can be reliable and yet entirely inexplicable. Local reality versus global constraint. The signal obeys local conservation laws but violates global expectations. Within a detector, it is consistent. When scaled to universal principles, it is incompatible. Reality appears layered, coherent in one frame, contradictory in another. Each measurement seems perfectly logical in isolation, yet the broader context exposes cracks in the framework. It is as if the universe plays by two rule books at once, one precise and reliable, the other indifferent to the first. Within the controlled environment of laboratory instruments, all readings conform. Energy balances, momentum exchanges, and particle interactions follow the familiar dance dictated by known laws. Scientists can predict behavior, repeat experiments, and reproduce outcomes. In this microcosm, the signal is entirely intelligible. It respects the constraints set by its immediate surroundings. It behaves, but only locally. Step outside that frame, however, and coherence begins to fracture. When the same signal is interpreted in the context of universal principles, cosmological energy balances, galactic scale interactions, or quantum field expectations. It no longer fits. Conserved quantities appear violated, symmetry is broken, and established relationships undone. The local order, so reassuring in its immediacy, becomes a deceptive veneer. What was once predictable now hints at inconsistency, suggesting that the rules we consider universal may have limits, boundaries, or contextual dependencies we have yet to comprehend. This layering of reality forces a re-evaluation of what laws mean. Are they absolute, governing all scales with uniform authority, or emergent, reliable only under specific conditions? The idea of emergent rules has precedent in physics. Temperature arises from particle motion, pressure emerges from collisions, and classical mechanics approximates quantum behavior. Yet the phenomenon at hand challenges this concept to a new degree. It is not a mere statistical effect or approximation. It is a direct, measurable deviation. The universe allows local consistency while denying global conformity, a duality that tests both mathematics and intuition. Interpretation becomes a delicate exercise. Scientists must ask whether these layers of reality are separate but non-interacting, or whether their contradictions are telling a deeper story about how the cosmos organizes itself. Could there be hidden mechanisms that reconcile the local and global, like subtle compensations beyond current detection? Or is the universe fundamentally multi-scale, a mosaic in which what is coherent on one level may be paradoxical on another? The signal suggests that observation alone may never yield a complete picture. Comprehension may require frameworks capable of holding contradictory truths simultaneously. The consequences are philosophical as well as practical. Much of physics is built on extrapolation. Local observations inform models of stars, the galaxies, and cosmic evolution. If local consistency does not guarantee global validity, then every assumption about large-scale dynamics becomes provisional. Predictions about energy flows, particle behavior, and even the structure of space-time must be re-examined. Layered reality implies that knowledge has limits, not merely of precision, but of scale, that understanding something here does not automatically mean understanding it there. This signal, precise in isolation, yet defiant in totality, embodies a profound tension at the heart of scientific inquiry. It is a reminder that reality is not monolithic. Coherence is conditional, universality is uncertain, and the apparent simplicity of laws may conceal a hidden stratification of principles. Local truths may thrive in their own domains, while global coherence remains elusive. In the subtle measurements of modern instruments, we glimpse a cosmos that is at once orderly and rebellious, a universe that asks not just for observation, but for a new imagination capable of holding contradictions. In the end, the phenomenon forces humility. It demonstrates the consistency in one frame does not guarantee comprehensibility in another. The layers of reality coexist, sometimes in harmony, sometimes in tension, challenging the notion that the universe is fully knowable. Local reality offers comfort. Global constraints demand wonder, and it is in navigating the space between these layers that our understanding of the cosmos deepens, however uneasily. Decay patterns that refuse. Understanding particles decay according to precise rules. This particle decays differently. Its byproducts align in ways that suggest a hidden mechanism, one not accounted for in any model. Measurement confirms it. Understanding cannot. Every collision, every decay event reinforces the anomaly. The universe permits behavior that the established frameworks of particle physics cannot predict. The decay is neither random nor chaotic. It is systematic, yet the system is invisible, its rules unreadable. Scientists detect patterns, yet those patterns resist explanation, as if the universe has hidden a chapter of its own instruction manual. Repeated experiments reveal the decay's consistency. Detectors record energy, distributions, spin orientations, and momenta of decay products that repeatedly diverge from expectations. Statistical analysis confirms the effect beyond reasonable doubt. Still, no theoretical adjustment, no extension of the standard model, no introduction of exotic particles, no quantum correction fully captures the observed sequence. It is as if the particle obeys a set of laws that exist parallel to, but separate from, the known framework. Each measurement deepens the puzzle, exposing the limits of even the most precise instrumentation and the most sophisticated simulations. The subtlety of the effecto amplifies its intrigue. Unlike dramatic events such as particle collisions at extreme energies, this decay occurs quietly, invisibly, yet its consequences ripple outward. The pattern of byproducts forms correlations across space and time, hinting at a hidden connectivity in the fabric of reality. Observers are forced to confront the possibility that some processes operate behind the veil of direct observability, that their influence apparent only through secondary or tertiary effects. The universe, in this respect, behaves not as a fully transparent system, but as a layered one, each layer interpretable only with specialized tools, patience, and imagination. Attempts to model the decay have introduced speculative mechanisms, hypothetical forces, hidden dimensions, even interactions with as yet undetected fields. These ideas account for fragments of the behavior, yet none reconstructs the entirety of the phenomenon. The particle seems to inhabit a liminal space between known and unknown, obeying a logic that is internally coherent, yet alien to current understanding. It is a reminder that physical law, while remarkably robust, is not synonymous with completeness. Observation can reveal more than theory can encompass. The philosophical implications extend beyond physics. If decay processes can operate under hidden rules, then reality itself may be more intricate than previously imagined. Determinism, causality, and even the concept of isolated events become fluid, suggesting that interactions may be influenced by structures or principles not yet accessible to human inquiry. The anomaly emphasizes that our models, though powerful, are approximations, maps of reality, not reality itself. Each unexpected decay is a whisper from the universe, a subtle indication that understanding is provisional, that knowledge is emergent rather than absolute. In practical terms, the decay challenges experimental, design, and interpretation. Laboratories worldwide calibrate, cross-check, and verify data to ensure that no error or artifact produces the anomaly. Yet every iteration confirms the result. Scientists speak of persistent deviation, covert symmetry, or hidden coupling, but these are descriptors, not explanations. They signal respect for the phenomenon rather than mastery over it. It is a patient, persistent, and profoundly humbling confrontation with the unknown. Ultimately, the particle's mysterious decay is not merely a curiosity, it is a gateway. It provokes the question of what other hidden processes might exist, quietly shaping matter, energy, and information. By defying understanding, it expands the horizon of inquiry, compelling science to evolve, adapt, and imagine beyond the boundaries of current theory. In these subtle departures from expectation, the universe quietly insists that its deepest truths are not always the most visible ones. That comprehension requires both precision and humility. The silent influence on surroundings, although subtle, the signal interacts with the environment. Fields shift, nearby particles respond. It is not an isolated anomaly. Its existence imprints itself on reality in measurable ways, yet without producing dramatic phenomena. Its effects are pervasive precisely because they are quiet. Unlike cosmic events that announce themselves with bursts of light or shockwaves of energy, this influence operates in the background, adjusting the local landscape with a near invisible hand. Particles deviate from expected paths, energy distributions fluctuate slightly, and fields exhibit minor perturbations, all detectable only with the most sensitive instruments. Yet cumulatively, these micro-adjustments can guide the evolution of systems in ways that are far from negligible. Consider a region of interstellar gas. On a superficial level, it appears uniform, subject only to gravity and radiation pressure. But the signal subtly alters particle trajectories, nudging distributions toward unexpected configurations. Over millennia, these tiny nudges can lead to density patterns that would not arise under standard assumptions. Stars form along slightly shifted filaments, clusters develop asymmetries, and magnetic fields orient differently than predicted. The influence is silent, but it shapes the structures that emerge, leaving a hidden fingerprint in the architecture of the cosmos. At the quantum scale, the effects are even more paradoxical. Particles respond not through collisions or forces in the classical sense, but through adjustments in probability distributions. The signal alters likelihoods, biases certain states over others, and modulates interactions without producing any detectable explosion of energy. It is a form of control that is invisible to the naked eye, measurable only through statistical accumulation. Entanglement, superposition, and tunneling all carry subtle signatures of this hidden hand, revealing a reality where influence does not always announce itself with drama. This subtlety challenges the assumptions underlying experimental physics. Standard methods often rely on abrupt or large-scale events to identify causal relationships. But here, causality is diffuse. The signal spreads influence gradually, producing measurable outcomes only in aggregate. The effect is like wind shaping sand dunes. Each gust alone is imperceptible, yet over time, the landscape is irrevocably altered. Similarly, the signal operates quietly, leaving reality subtly rearranged in ways that accumulate and propagate. Philosophically, this raises questions about perception and significance. Humans tend to notice only the obvious, the sudden, the spectacular. But the universe may harbor forces whose importance lies precisely in their silence. The signal demonstrates that influence does not require loudness. The small and persistent can produce meaningful change. It calls attention to a dimension of reality in which subtlety is the primary mode of power, where the unseen consistently reshapes the seen. Experimentally, detecting this influence requires extraordinary care. Instruments must distinguish between background noise and genuine perturbations, and repeated measurements are necessary to confirm that the deviations are systematic rather than coincidental. Yet even with perfect data, interpretation is nuanced. The signal's effects are distributed, contingent, and interwoven with the broader fabric of interactions. The task is not merely to observe, but to disentangle the contribution of this silent influence from countless other forces at play. Over time, the accumulation of these minor perturbations can manifest at scales far beyond the microscopic. Entire regions of space may display structural preferences. Cosmic phenomena may emerge along trajectories subtly favored by these interactions, and energy flows may become skewed in ways not accounted for by conventional models. The universe, in other words, responds quietly yet persistently, guided in part by influences that refuse spectacle but insist on presence. Ultimately, the signal reframes our understanding of causality and impact. Influence need not be overt to be real. Presence need not announce itself to matter. Reality is layered, responsive, and receptive to subtlety. The silent influence on surroundings exemplifies a universe where even the faintest whispers of force leave enduring traces, quietly shaping the cosmos without demanding recognition, yet shaping it all the same. Beyond probability, quantum mechanics allows for uncertainty within defined probability distributions. This signal exists in a state that probability itself cannot fully describe. It is not an outlier, it is a statistical impossibility made real. At every level, the data defies expectation. Calculations that should yield negligible likelihood instead reveal persistent, repeatable results. Classical probability provides no framework to accommodate such events, and even the probabilistic models of quantum theory, those designed to tolerate uncertainty, strain to account for the phenomenon. The implication is profound. The universe can manifest realities that conventional statistical reasoning deems impossible. The anomaly is not chaotic, nor is it random in the colloquial sense. Its behavior exhibits consistency, a coherence that betrays an underlying structure beyond current understanding. Like an uncharted coordinate on a familiar map, it occupies a space that theory predicted should be empty, yet it is there, measurable and undeniable. Repetition across experiments confirms its robustness, while statistical analyses reveal that the odds of coincidence are vanishingly small. This is a signal that defies probabilistic boundaries, a manifestation of order that exceeds the constraints of known mathematics. Consider the implications for how you define possible. In quantum mechanics, superpositions allow multiple outcomes to coexist until observation collapses the system into a single result. Yet even superposition is bounded by probability amplitudes. Here, the effect transcends those bounds. It suggests that the universe is not merely probabilistic, but capable of creating events that challenge the very meaning of probability itself. The anomaly is a reminder that the mathematical tools humans construct, tools meant to quantify uncertainty, are still approximations, shadowing a reality richer and stranger than any model predicts. The phenomenon also challenges notions of causality. Classical cause and effect relationships rely on the predictability of outcomes within defined probabilities. When a statistical impossibility becomes actual, the familiar chain of expectation falters. How can an event occur that probability forbids? The answer may lie in hidden correlations, in dimensions or variables that evade current measurement, or in principles of nature that have yet to be discovered. Whatever the mechanism, the universe demonstrates that its rules are not as fixed as they appear. Even the impossible is permitted under conditions that are not yet understood. Equally striking is the signal's persistence across contexts. When replicated under varying experimental conditions, it maintains its character. It is not a fluke of equipment, an artifact of sampling, or an anomaly restricted to a single trial. Instead, it points to a fundamental property, a layer of reality where statistical expectations are subordinate to a deeper, subtler order. Recognizing this requires abandoning the comfort of well-defined probability spaces and embracing the uncertainty that exists even beyond uncertainty itself. Ultimately, this is more than a challenge to mathematics. It is a challenge to perception. Human intuition is built upon patterns, regularities, and the predictability of outcomes. When confronted with a statistical impossibility that manifests, perception must adapt. You are forced to consider a universe in which events are not merely governed by probability, but by principles that allow exceptions so profound they redefine the framework of possibility. This is not chaos, nor randomness without structure. It is a new category of order, one that exists beyond the reach of conventional probability, a reminder that reality can, and does, transcend the limits of expectation. In the end, the signal demands recognition of the extraordinary. It is not an error, nor a rare anomaly to be dismissed. It is a phenomenon that exposes the limitations of current models, a statistical impossibility made tangible, insisting that you expand your understanding of what is real, what is probable, and what is possible. Beyond probability lies a reality where even the impossible can exist. Then where the universe continues to quietly exceed the bounds of human anticipation. Entanglement of expectations. Your theoretical predictions entangle particles across distance and time, yet this detection entangles outcomes with assumptions. Observations you make are influenced by the signal's mere presence, quietly reshaping what can be measured. In quantum mechanics, measurement is not a passive act. Observing a particle collapses a superposition, determining one outcome among many possibilities. On cosmic scales, the principle is not literal in the same experimental sense, but the analogy illustrates a subtle truth. The act of observation imposes structure on the data you collect. The instruments, models, and calibration choices you employ influence how signals are interpreted, especially when those signals are faint, distant, or temporally remote. When measuring expansion, the effect is cumulative. Early universe probes rely on the cosmic microwave background, whose fluctuations encode conditions from 380,000 years after the Big Bang. Extracting parameters from that signal requires assumptions about energy densities, initial perturbations, and the physics governing recombination. Each assumption constrains what counts as a valid measurement. The act of interpreting the data is entangled with the framework applied, shaping the apparent expansion rate. Similarly, local measurements rely on standard candles, distance ladders, and calibration hierarchies. Every rung introduces potential bias, however minute, and the process of interpretation filters outcomes through assumptions about stellar physics and light propagation. Even a perfectly executed observation is not entirely independent. Its meaning is constructed in relation to theoretical expectations. The universe does not announce numbers directly. It provides photons and gravitational signals, which humans translate into cosmological parameters. That translation is inherently entwined with presuppositions. The entanglement becomes more pronounced when these measurements are compared. Each framework is internally consistent. The early universe value for the Hubble constant aligns with its assumptions and constraints. The late universe value aligns with a different set. Yet when juxtaposed, a divergence emerges. This divergence is not necessarily evidence of error or failure. It may reflect the subtle influence of assumptions embedded in each observational method. Measurement is not independent of theory. It interacts with it, reinforcing internal consistency while revealing inter-framework tension. Precision amplifies this entanglement. As instruments improve, subtle dependencies between assumptions and observed outcomes become more consequential. Tiny deviations that were once masked by uncertainty now emerge as statistically significant. Error bars shrink, but the underlying coupling of observation and expectation remains. The tension grows sharper precisely because precision exposes the latent influence of assumptions, revealing inconsistencies that were always present but invisible under coarser measurement. There is also a temporal dimension. Light from distant galaxies arrives after billions of years, carrying information shaped by the universe's evolving expansion. Interpreting that signal requires extrapolation across epochs. Each step of inference assumes uniform physical laws, consistent cosmic composition, and predictable gravitational dynamics. Any deviation from these assumptions subtly affects the resulting parameters. The act of observation is therefore entangled not only with assumptions in the present, but with assumptions projected across cosmic time. This entanglement is not merely a technical concern, it is conceptual. The divergence between early and late universe expansion rates may partly arise from the complex interplay of data, interpretation, and expectation. Observations are not purely given. They emerge through a structured process influenced by what you assume the universe should be. Measurement and model, signal and expectation are inseparable. Yet this does not imply arbitrariness. The data constrain theory, and the theory constrains interpretation. The entanglement defines the limits of what can be inferred with confidence. Within those limits, tension persists. The numbers are internally consistent, yet collectively discordant. Each measurement is shaped by its context, yet each challenges the context of the other. The universe, in this sense, is not contradictory. It allows precise, reproducible observation while exposing the limits of human frameworks. The entanglement of expectations ensures that understanding expansion is never merely a passive recording of reality. Observation interacts with assumption, measurement shapes interpretation, precision illuminates tension. The Hubble discrepancy, quietly persistent, is a product of this entangled relationship between the cosmos and the frameworks we use to understand it. The limits of observation. Even as instruments improve, some aspects of the signal remain opaque. It exists, you can measure it, yet full comprehension eludes direct observation. Reality continues to withhold its structure from the most precise tools. Every refinement in detection, every enhancement in sensitivity reveals detail only to obscure the larger pattern. The signal is real, persistent, undeniable, but its essence slipped through the grasp of measurement. It is simultaneously present and elusive, tangible and mysterious, like a shadow defined only by what it conceals. Attempts to map it reveal partial truths. Within constrained contexts, patterns emerge. You can describe behavior, chart frequency, quantify energy, and then trace interactions, but only locally. Every observational window offers a glimpse, a partial layer, yet the totality resists synthesis. The signal behaves predictably in controlled environments, yet its full architecture, its relation to broader systems, its origin and ultimate trajectory remains inaccessible. Observation hits a horizon, not of distance, but of principle, a limit beyond which instruments cannot extend without losing meaning. This opacity is not simply technical. It is structural, woven into the nature of reality itself. The universe, it seems, does not yield all at once. Knowledge is incremental, contingent, and inherently constrained by the frameworks we impose. Each tool, no matter how advanced, captures only a slice of the phenomenon. The rest is inferred, hypothesized, and model-dependent. Even when multiple instruments cross-verify data, the full structure remains concealed, a puzzle that is as much about the limits of human methodology as about the universe it interrogates. The signal's resistance to complete observation highlights a tension at the heart of science, the desire for comprehension versus the universe's inherent indeterminacy. Instruments can detect effects with astonishing precision, yet their interpretations remain provisional. The act of measurement illuminates, but it also exposes gaps. It is a reminder that observation is not synonymous with understanding, that seeing is not the same as knowing. Each successful detection brings confidence, yet simultaneously underscores the boundaries of insight. Speculation arises, informed by both theory and analogy. Perhaps the signal interacts with hidden dimensions, or with structures beyond space-time as we conceive it. Maybe it is governed by rules only partially compatible with known physics, accessible only indirectly through its consequences rather than its form. The opacity suggests a layered reality. What is measurable in one frame is inscrutable in another. A multi-scale architecture that cannot be flattened into a single descriptive model. The tools of observation, however sophisticated, engage only the surface of this architecture, hinting at depth but never fully revealing it. This limitation also shapes the narrative of discovery. Scientists are forced to work in partial knowledge, building models that approximate reality while acknowledging their incompleteness. The signal teaches patience, humility, and restraint. It is a reminder that even in the era of extraordinary instrumentation, telescopes capable of seeing back to the universe's infancy, detectors sensitive to subatomic tremors, some truths remain elusive. Nature does not reveal all at once. It withholds, suggesting structure and pattern without granting full comprehension. Ultimately, the limits of observation are not failures. They are features of the cosmos. They define the boundary between what is immediately knowable and what is forever inferred. The signal exists in this threshold, measurable yet opaque, bridging presence and mystery. In observing it, humanity confronts the gap between perception and understanding, between the reality that can be quantified and the deeper order that remains concealed. The universe is precise enough to be detected, the subtle enough to resist full explanation, and persistent enough to demand continued inquiry. Within these constraints, knowledge grows not by certainty, but by navigating the margins of what can be seen and what remains beyond vision. Consistency, without explanation. The data is internally consistent. There are no errors, no misreads, yet consistency does not imply comprehensibility. You are confronted with a pattern that obeys no model other than its own persistence. Every measurement, across instruments and experiments, confirms the same structure, the same sequence of events, the same correlation of variables. There is no noise to dismiss, no statistical fluke to attribute it to. The pattern is real, undeniable, and yet it defies any framework designed to explain it. It exists in a space between certainty and understanding, a territory that science recognizes but cannot fully chart. Attempts to analyze it follow every standard protocol. Calibration, cross-validation, redundancy checks, everything confirms that the data is accurate. Multiple teams replicate observations, multiple methodologies converge on the same outcome, yet the anomaly remains resistant to interpretation. The consistency is paradoxical. It reassures by its reliability, yet frustrates by its opacity. This is not chaos masquerading as order. It is order without reference, a self-contained logic that insists on being measured even as it refuses to be comprehended. The phenomenon is subtle in its manifestation. It is not a dramatic spike or an overt deviation that draws immediate attention. Instead, it is a faint but persistent alignment, a recurring resonance across datasets, and a regularity that is both predictable and inexplicable. Scientists find themselves tracing its outline, examining its parameters, and discovering repeatedly that each thread of analysis loops back on itself without yielding a bridge to existing theory. It is a reminder that consistency, while necessary for credibility, is not sufficient for understanding. Models, simulations, and hypotheses have all been tested. Each provides partial insight, yet none captures the complete pattern. Some suggest hidden variables, some propose unknown interactions, some invoke principles that may operate at scales or dimensions beyond direct observation. All fail to fully reconcile the empirical evidence. The pattern seems to obey rules of its own design, a self-contained architecture that does not intersect with known frameworks. In that respect, it is profoundly alien, familiar in its reliability, foreign in its logic. The subtlety of the anomaly compels patience. Unlike phenomena that shock or overwhelm, this consistency demands sustained attention, careful accumulation of evidence, and long-term study. Each data set reinforces the pattern, and each replication confirms that the phenomenon is not transient. In its quiet persistence, it reshapes the experimental approach. Measurement must be meticulous, observation continuous, and interpretation open-ended. Understanding cannot be rushed. It arrives, if at all, only through the slow unfolding of persistent inquiry. Philosophically, the pattern provokes reflection on the limits of knowledge. It suggests that reality may contain layers of regularity inaccessible to conventional models, that even complete information may not equate to comprehension. The universe, in this sense, operates not only according to observable rules, but also through hidden architectures whose logic can only be inferred indirectly. Consistency, without explanation, forces a reconsideration of of what it means to know something and reminds observers that certainty and comprehension are not always aligned. Ultimately, the phenomenon is both a challenge and an invitation. It confirms that the universe can produce order independent of human understanding, that it can obey principles that transcend familiar frameworks, and that the pursuit of knowledge must account for patterns that are internally coherent, yet externally inscrutable. In confronting this consistency without explanation, the science is reminded of its own humility. Reliable observation does not always yield meaning, and the universe retains the power to surprise even in its most orderly gestures. The unseen framework. Perhaps the universe contains a framework hidden from all prior measurement. The signal suggests a layer beneath the standard model, imperceptible until this precise moment, measurable but previously invisible. This hidden layer is neither random nor chaotic. It exhibits structure, subtle yet pervasive, guiding interactions in ways that only now become apparent. Where the standard model provides rules for particles, forces, and fields, this unseen framework seems to provide context, an underlying architecture that shapes outcomes without itself being directly observable. It is not an additional force in the conventional sense, but a scaffold, a template woven into the fabric of reality that subtly constrains and channels phenomena. The implications are profound. If the universe possesses this additional framework, much of what we consider fundamental may be emergent. Properties of particles, the apparent uniformity of forces, even constants long assumed immutable could arise as consequences of this hidden layer. What we measure is not raw reality, but reality filtered through the framework's subtle influence. Our experiments, precise though they are, may have been probing only projections, shadows cast by a deeper organizational principle. At the quantum scale, the effects manifest as surprising correlations. Particles appear to know more than their local environment would suggest. Entangled states, tunneling phenomena, and probability distributions acquire patterns previously unexplained, hints that the unseen framework mediates interactions in ways that remain hidden until aggregated over time and space. These are not dramatic violations of established physics, but whispers of a deeper order, a connective tissue that links outcomes with invisible consistency. Cosmologically, the framework could explain the subtle uniformities and irregularities observed across vast distances. Galaxies align along filaments that suggest directionality beyond simple gravitational clustering. Cosmic microwave background fluctuations, long treated as statistical anomalies, may carry imprints of this underlying structure. The universe's large-scale geometry, its expansion patterns, and even the distribution of dark matter could be reflections of this hidden layer, a scaffolding that organizes without announcing itself. Theoretical attempts to model such a framework face immense difficulty. Traditional approaches rely on observable quantities and measurable forces, but here the framework exerts influence precisely by evading direct detection. Mathematicians and physicists are compelled to think in abstractions, topologies that encode constraints without forces, higher dimensional lattices that subtly bias interactions, or network-like structures embedded in the quantum vacuum. The challenge is not just to describe what is visible, but to infer what must exist beneath the surface to produce the observations we now record. Experimentally, the detection is delicate. Measuring this layer requires teasing out systematic deviations from expected behavior, de-isolating influences too small to trigger conventional responses. Each confirmed effect is a clue, a fragment of the larger architecture gradually revealed. It is a painstaking process, but the signal persists, undeniable in its consistency, even as it refuses to declare its full scope. Philosophically, the existence of an unseen framework reframes our understanding of knowledge itself. Reality may be far richer than the instruments we build, far more organized than the rules we can formalize. The universe is not simply a collection of particles and forces, but a layered construct with visible phenomena emerging from hidden scaffolds that dictate the possible. The framework's subtlety is its signature. It shapes without spectacle, organizes without direct manifestation, and governs without appearing to govern. Ultimately, the unseen framework suggests a cosmos where what is measurable is only part of the story. Beneath the surface of known physics lies a structure both elusive and real, quietly orchestrating interactions, guiding the evolution of matter, and offering a hidden coherence that unites phenomena previously treated as independent. To recognize it is to glimpse the universe not only as it appears, but as it truly is. A layered, interconnected tapestry with depth, order, and subtlety extending beyond the reach of prior understanding. Scale and the unexpected. You assume scale informs behavior. Microscopic interactions aggregate into macroscopic predictability. This particle suggests a breakdown of that assumption, where a single measurement disrupts patterns across expected scales. It is not merely an anomaly confined to a laboratory setting. Its influence propagates, subtly altering outcomes across systems previously considered independent. What is striking is not the particle itself, but the way it exposes the fragility of hierarchical assumptions, the illusion that small-scale order inevitably dictates large-scale coherence. At first glance, this behavior might seem isolated, an outlier in a sea of otherwise predictable phenomena. Yet repeated observation confirms its consistency. Each interaction echoes across scales in a manner that challenges conventional, statistical, and physical frameworks. The macroscopic world, normally resilient to the fluctuations of individual components, reacts in ways that are measurable and repeatable. This is not noise masquerading as signal, nor is it a transient anomaly. It is a persistent, irreproducible phenomenon that forces re-evaluation of how scale, causality, and aggregation are understood. The implications extend to foundational assumptions in physics and mathematics. The principle that the behavior of a system can be approximated by averaging its constituents, the very idea that underpins thermodynamics, statistical mechanics, and even emergent properties in complex systems, is called into question. Here, the particle acts as a singular agent, a disruptor whose effect is disproportionate to its size. It suggests that under certain conditions, interactions at the smallest scales can reverberate in ways that are not merely amplified, but qualitatively transformative. Predictability becomes contingent, not guaranteed. Consider analogous effects in other domains. In chaos theory, small perturbations can lead to vastly different outcomes, the so-called butterfly effect. But even there, the underlying system dynamics remain deterministic. What this particle demonstrates is different. It introduces disruption that cannot be reconciled with standard models of propagation or amplification. Its impact is not an exponential divergence of expected trajectories. It is a fundamental, nonlinear alteration of behavior across scales. The result is a universe that refuses to be neatly partitioned into micro and macro, where the boundaries of influence are more porous and intertwined than previously imagined. This scaling anomaly also forces a reconsideration of measurement itself. Observing the particle influences outcomes, but not in the simple, local way described by standard quantum measurement. Its effects permeate across levels, so that the act of measurement in one domain can shift statistical relationships elsewhere. The distinction between cause and effect, local and global, small and large, becomes blurred. What was assumed to be a hierarchy of scales, where order at one level emerges predictably from the level below, must now be understood as conditional, provisional, and sometimes violated. Beyond physics, the conceptual consequences are profound. Scale has long been a tool for simplifying complexity. By assuming that macroscopic patterns arise from microscopic regularities, humans construct models of everything from chemistry to climate, from economics to biology. But when a single element defies that assumption, it is a reminder that simplification is always provisional. Reality, at its extremes, that can resist reductionist expectations, insisting that the behaviors of its smallest constituents sometimes resonate unpredictably throughout the larger system. Ultimately, the particle serves as both a challenge and an invitation. It challenges deeply held notions of aggregation, emergence, and hierarchy. It invites exploration of a universe in which scale is not a guarantee of order, but a context-dependent lens, one that may obscure as much as it reveals. Predictability is no longer absolute. It is fragile, emergent, and occasionally disrupted in ways that demand new frameworks of understanding. The unexpected influence of a single particle reminds you that the structure of reality is more intricate than any map of scales can fully capture. In this revelation lies both caution and possibility. The universe remains coherent, yet it can surprise in ways that defy the assumptions you once trusted. A signal that questions reality. The detection forces a confrontation with what you accept as real. If a particle can exist in defiance of models, what does that imply about the completeness of your understanding of matter, space, and time? In classical physics, reality is assumed to be deterministic and predictable. Objects have defined positions, velocities, and properties that obey measurable laws. Quantum mechanics shattered that intuition at microscopic scales, but you carry the classical expectation into cosmology. You expect the universe to behave consistently, to yield measurements that can be reconciled into a coherent model. Yet the appearance of a particle or any signal that contradicts established predictions challenges that expectation directly. The particle's behavior may not break laws outright. It may conform locally, obeying interactions in conservation rules in observed experiments. Yet globally, its existence strains frameworks. A particle that influences expansion, alters energy distribution, or contributes undetected degrees of freedom undermines assumptions embedded in the standard model of cosmology. Its effects are subtle enough to have eluded direct detection until precise measurement, yet substantial enough to influence inferred expansion rates. In this way, reality itself appears more nuanced than your models suggest. Observations are forced into a dialogue with theory. Every detected anomaly must be interpreted. Does it reflect unknown physics, a statistical fluctuation, or an unrecognized systematic? In the case of a particle influencing cosmological expansion, the question is not speculative. It is grounded in observed tension between independent measurements. The particle would not merely expand your knowledge, it would reveal that your prior conception of the universe's contents and dynamics is incomplete. The frameworks you rely upon, though successful across vast scales, are now partial maps rather than complete descriptions. The implications extend beyond matter to space and time. If an unknown particle subtly affects expansion, it demonstrates that the universe's evolution is contingent on components you had not considered. Space itself expands according to the total energy momentum content of the cosmos. A new particle modifies that content. Consequently, time-dependent measurements, distances between galaxies, light travel, and the chronology of structure formation carry an embedded effect of this unobserved entity. The apparent history of the cosmos, inferred from photons traveling billions of years, is partially shaped by a component previously unrecognized. Furthermore, this detection underscores the inseparability of observation and reality. Measurements do not merely reveal pre-existing values. They confront you with anomalies that force reinterpretation. The universe does not simplify to fit expectations. It presents signals in their true complexity, leaving you to reconcile them with models constructed from prior assumptions. The particle is a subtle punctuation mark in the narrative of cosmology. Small, almost invisible, yet with consequences that ripple through the framework of understanding. Conceptually, it challenges your expectation that matter, space, and time are fully accounted for by known laws and particles. It implies that completeness is provisional. What you regard as fixed, constants, components, interactions, may only be effective descriptions, approximations valid within a limited domain. Reality, in its totality, may contain elements that influence observable outcomes while remaining largely hidden. These elements may explain tensions in expansion, subtle anomalies in structure formation, or even deviations in gravitational behavior across cosmic scales. The signal also emphasizes caution in interpretation. It does not provide immediate answers. It highlights incompleteness without specifying mechanism, quantity, or interaction. It is simultaneously precise and elusive, measurable in its effects, inscrutable in its full nature. Its existence forces a reassessment of what is assumed fundamental, of the boundaries between observed and inferred, of the scope of cosmological knowledge. Ultimately, a particle that defies models is more than an anomaly. It is a reflection of the universe's capacity to exceed expectation. It reveals that reality may not simply conform to frameworks that appear coherent locally. The cosmos may be ordered in ways that are internally consistent but globally richer and more intricate than current models capture. The detection does not answer questions, it deepens them, forcing acknowledgement that matter, space, and time are structured with subtlety and complexity beyond immediate measurement. The persistence of the unexplained. Over weeks, months, and years of repeated experimentation, the signal endures. Persistence suggests law, yet law itself seems insufficient. Reality contains behavior that is both stable and inexplicable. It is measurable, repeatable, and yet defies classification. Instruments detect it with unwavering consistency, yet no theory fully accounts for it. The anomaly is both mundane in its reliability and extraordinary in its resistance to understanding, a paradox embedded within the fabric of observation itself. The longevity of the signal challenges assumptions about randomness, noise, and chance. Most anomalies fade with scrutiny or are traced to error, yet this signal remains, unwavering and persistent. Its continued presence implies a hidden order, a rule or structure governing its behavior, but that rule is one we do not recognize. Conventional physics, even at its most flexible, they cannot accommodate its consistency alongside its defiance of expectation. The universe is revealing something repeatable, yet something entirely outside known principles. Persistence also reshapes the way experiments are conceived. Repetition is no longer a mere validation technique. It becomes a form of dialogue with an unyielding phenomenon. Each iteration uncovers nuance, minute variations, correlations, or thresholds, but the overall pattern remains resistant to reduction. Researchers are compelled to ask questions beyond mechanics. Why does the signal exist? What does its endurance imply about the structures of reality that allow it to persist? Each answer generates further mystery, and each measurement emphasizes that stability does not equal comprehensibility. This signal's constancy hints at a deep-seated coherence within the universe, but one that is inscrutable. Stability is usually a sign of causality, of predictable rules, yet here it coexists with unpredictability. The phenomenon respects no hierarchy of explanation. It is simultaneously ordinary and anomalous. Its endurance forces a re-evaluation of what law means. Perhaps natural law is not a monolith, but a spectrum, robust locally, yet incomplete globally. Perhaps the universe permits persistent exceptions that operate under principles we have yet to articulate. The persistence also raises profound epistemological questions. If something can endure, be reproducible, yet remain fundamentally unexplained, what does that imply about the limits of human comprehension? Our instruments can measure it, then our mathematics can describe aspects of it, yet understanding, true grasping of cause and effect, remains elusive. The universe permits us to interact with patterns we cannot fully explain, revealing the delicate boundary between observation and knowledge. Persistence without explanation challenges the assumption that repeated phenomena must ultimately be reducible to known laws. Speculation naturally emerges. Could the signal be a manifestation of hidden dimensions, operating according to constraints beyond current perception? Might it represent a subtle structure in space-time, a persistent trace of processes invisible to direct measurement? Or is it a feature of reality itself, an enduring phenomenon whose purpose is not functional but intrinsic, a persistent thing whose existence does not require full understanding? Each hypothesis expands the imagination while emphasizing the tension between persistence and comprehension. Ultimately, the signal's endurance is both a beacon and a warning. It illuminates the persistence of mystery at the heart of the cosmos, showing that even with perfect tools and rigorous methods, some behavior will not yield. Stability and inexplicability coexist, revealing a universe that is orderly enough to measure yet chaotic enough to resist full explanation. The unexplained does not disappear with observation, it persists, a reminder that the universe contains principles and phenomena beyond immediate understanding. It is a phenomenon that commands attention, demands patience, and insists on humility. Proof that even repeated measurement cannot guarantee comprehension, and that some truths endure as enigmas, the quietly persistent within the architecture of reality. Measurement as revelation. Measurement is not a passive act. It reveals limits, exposes contradictions, and confronts you with phenomena that cannot be framed with an existing understanding. The signal demonstrates that observation itself is an active dialogue with the unknown. Each reading, each data point is both a confirmation and a question, a tether to reality that simultaneously illuminates and obscures. To measure is not merely to collect information, it is to interact with the structure of the universe, to provoke a response, and to confront the boundaries of comprehension. Across laboratories, detectors, and observatories, the signal persists. Its presence is undeniable, yet its implications resist simplification. Instruments capture oscillations, shifts, then subtle correlations that defy existing models. Patterns emerge, but they do not map onto familiar frameworks of causality, energy distribution, or particle interaction. Each repetition of the measurement reinforces its reality while deepening the mystery. The act of observation becomes a conversation with something that has its own rules, rules that remain hidden even as their effects manifest. The subtlety of the signal highlights the active role of measurement. Unlike events that announce themselves dramatically, collisions, bursts, or explosions, this phenomenon requires patient engagement. Scientists must calibrate, cross-check, and refine instruments, often over extended periods, to perceive it clearly. In this sense, the process of measurement is inseparable from the phenomenon itself. It is only through careful, then persistent interaction that the anomaly reveals its structure, yet even then, revelation is partial, tantalizing, and incomplete. The philosophical implications are profound. Measurement exposes the limitations of human understanding, illustrating that data alone cannot produce comprehension. A reading can be precise, repeatable, and internally consistent, yet still point to processes that evade explanation. This challenges the traditional notion that observation simply uncovers what is already there. Instead, it suggests that reality, at its deepest levels, requires dialogue. The act of probing elicits responses that are contingent, context-dependent, and sometimes paradoxical. Measurement becomes a bridge between the known and the unknowable, a method for mapping the contours of reality without ever fully defining it. In practice, this dynamic reshapes scientific methodology. Experiments are designed not only to test hypotheses, but also to interrogate the limits of instrumentation and interpretation. The observer cannot be entirely neutral. Choices of sensitivity, duration, and parameterization influence what is revealed. This interplay underscores that science is an active process, one in which the act of measurement shapes the phenomena under scrutiny. The signal itself embodies this principle. It emerges only in response to specific forms of interaction, persisting across contexts, while remaining resistant to full articulation. The signal's persistence invites reflection on the nature of reality itself. If measurement can reveal contradictions and patterns beyond comprehension, then the universe may harbor structures that operate independently of our conceptual frameworks. Observation becomes not merely a tool for cataloging events, but a means of engaging with hidden architectures of existence. Each data point is simultaneously a mirror and a window. It reflects the constraints of our understanding, while offering a glimpse of what lies beyond. Ultimately, measurement as revelation is a call to humility and curiosity. It reminds us that certainty is provisional, comprehension is iterative, and the universe may always contain elements that resist reduction to familiar terms. The signal does not surrender its secrets willingly. It requires patience, precision, and a willingness to engage with the unknown on its own terms. In this dialogue, science is both challenged and inspired. It's compelled to navigate a landscape where every act of observation is also an act of discovery, and where the boundaries of knowledge are defined not solely by what we can measure, but by how measurement itself shapes the path to understanding. The question that remains: all data converges on a paradox. Something exists that should not. You are left with certainty and contradiction in equal measure. The universe presents you with evidence that your frameworks cannot contain, and no simple resolution is possible. This is not a fleeting anomaly or a glitch in measurement. The evidence is persistent, reproducible, and consistent across independent observations. Every experiment designed to test its existence returns the same impossible result. You confront a reality where known laws remain valid within their domains, yet fail when confronted with this outlier. It is a fracture in comprehension, a point where expectation and observation diverge, forcing a reckoning with the limits of understanding. The paradox operates at multiple scales. At the microscopic level, particles behave in ways that violate the standard symmetries and conservation rules you rely on. Interactions occur without apparent cause. Energy seems redistributed in ways that are improbable, and correlations appear between elements that should be independent. At the macroscopic scale, these subtle deviations aggregate, creating patterns in cosmic structures, in radiation backgrounds, and in field distributions that defy simple modeling. What is invisible to casual observation manifests unmistakably in accumulated data, revealing the persistence of the inexplicable. Mathematically, the situation is daunting. Equations that were once thought comprehensive now serve only as approximations, valid in restricted regimes, but inadequate to describe the totality of what is observed. Extensions of current models, supersymmetry, string theory, hidden dimensions, offer tantalizing hints, but provide no definitive explanation. The universe refuses to submit to theoretical neatness, insisting instead that its behavior can be coherent and incomprehensible simultaneously. Each model explains fragments, but cannot unify the paradox without introducing further assumptions themselves unverified and speculative. This confrontation with impossibility has philosophical implications as well. Science often assumes that inconsistencies signal gaps in knowledge that can be filled with better measurement or refined theory. Here, then, the inconsistency is fundamental. It suggests that reality is not fully reducible to rules or predictions, that certain phenomena may exist precisely because they lie outside established frameworks. Certainty coexists with uncertainty. Comprehension is incomplete, yet undeniable facts persist. You are forced to accept that the universe harbors truths that cannot be fully captured, at least not by methods that have served so reliably until now. Experimentally, this presents both challenge and opportunity. Observers must isolate the paradoxical phenomenon, verifying it across instruments, environments, and scales. Subtlety is key. Its effects are persistent yet understated, requiring careful attention to distinguish genuine signal from background noise. But within this subtlety lies insight, the opportunity to glimpse principles and interactions previously hidden, to expand the conceptual scaffolding of physics in directions unimagined. The paradox is both a barrier and a doorway, obstructing full understanding while pointing toward deeper truths. In a broader sense, the paradox reframes the act of observation itself. Measurements are no longer passive recordings of pre-existing reality. They are interactions with a universe that resists simplification, that contains structures beyond immediate apprehension. Evidence accumulates, but the interpretation remains contingent, provisional, and necessarily incomplete. Certainty in measurement coexists with uncertainty in meaning, producing a tension that is as intellectual as it is empirical. Ultimately, the question that remains is not one of simple resolution. The universe is offering a puzzle without a key, a truth without a narrative that can fully contain it. It challenges assumptions, undermines neat theoretical hierarchies, and insists on acknowledgement of what cannot yet be reconciled. In facing this paradox, you are compelled to expand the boundaries of inquiry, to imagine principles beyond current frameworks, and to accept that some aspects of reality may be both real and irreducibly mysterious. The universe has, in essence, handed you a certainty that defies closure, a profound reminder that the frontier of knowledge is defined not by what is known, but by the persistent questions that remain.